Okay, let's go ahead and begin. Okay, 16.5 is on curl and divergence. So we're going to set up some tools that we need for the next few sections. Okay, so we're going to set up some mathematical tools that we need. Okay, curl. Let's define what the curl is. Okay. If f is equal to pi plus qj plus rk is a vector field, on R3, and the partial derivatives of P, Q, and R exist, then the curl of F is the vector field on R3 defined by curl of F is equal to partial of R with respect to Y minus the partial of Q with respect to Z, I, minus the partial of R with respect to X minus the partial of P with respect to Z, J, plus the partial of Q with respect to X minus the partial of P with respect to Y, K. So that's what we call the curl. Okay. So let del equal, okay, again, this is del, okay, equal the partial of X with respect to I plus the partial of Y with respect to J, sorry, partial with respect to Y of J plus the partial with respect to Z of K. Okay, we call this the gradient operator. Okay, so if we cross del with F, okay, and what's F? Well, F again is I'll put F here. F is Pi plus Qj plus Rk. If we cross product this, then we can write this as Ijk as a 3x3 matrix. And we want to find the determinant of this 3x3 matrix. That's the cross product. And so we're going to say, well, we're going to cross del with F. So this is going to be d dx, d dy, and d dz. Okay. The partial with respect to x, the partial with respect to y, the partial with respect to z. And then we're going to have F, which is P, Q, and R. Okay, so this is equal to this whole thing is going to be equal to the curl of f. We'll see that in a second. That the the equation above can be generated from this 3 by 3 matrix. Okay, and that's how we're going to actually calculate the curl. Is we're not going to use the formula. We're just going to use the matrix. Okay, because it's just faster to calculate. Okay, so let's look at the ith value of this matrix. So we're gonna take this co-matrix or this cofactor. Okay, right there. If we look at the ith term, okay, of this determinant, then we're going to take and go dy of r, right, minus ddq or ddz of q, okay, I, okay, minus, okay, this is going to be ddx of r minus, okay, ddz of p, okay, j, and then plus, cross off the kth row and column, right? Oh, whatever. Okay, and we're going to get ddq, right? We go like this. Okay, dd partial with respect to x of q. Okay, minus the partial with respect to y of p. That's p. Okay, and then that's in the kth direction. Okay, so this is going to be equal to, right? We could just rewrite this partial of r with respect to y, partial of q with respect to z, I minus partial of r with respect to x minus partial of p with respect to z, j plus the partial of q with respect to x minus partial of p with respect to y. Okay, and look at that. That's the same thing that we got before. That's the curl. That's how we define the curl of f. The curl of f is the determinant of this 3 by 3 matrix of del crossed, okay, del crossed with f. Okay, that is the curl of f. Okay, so we can write that formally and say, look, the curl of f is equal to del cross f. Okay, you take f and you take the cross product with del, and that is your curl of f. And notice that this produces a vector field. This is a vector field. Okay, the original f was a vector field, and the curl of f is a new vector field. Okay, it's just going to give us new information. Okay, when we cross product these, we call it the curl. Okay, so let's go through an example. Let's find the curl of f mathematically here. Okay, if f of x, y, z, okay, we've got our vector field, is equal to xzi plus xyzj minus y squared k. Okay, then find the curl of f. Okay, so let's find the curl of this thing. So the curl of f is going to be our 3 by 3 matrix, I, j, k, ddx, ddy, ddz, and then we've got xz, that's our p, xyz is our q, and negative y squared is our r. So now we're going to take the determinant of this. So this is going to be the part, this is the partial with respect to x. Now I'll do that this time I'll write it all out, but normally I would just take this partial in my head. I would say, well, what's the partial of x? Oops, I'm doing this wrong. My bad. It's over here. Okay, what's the partial of negative y squared with respect to y? And then what would be the partial of this thing with respect to z? I would just do that in my head. Okay, if I want to find the ith term here. But I'll write it out formally. So this is d dy of negative y squared minus d dz of x, y, z. Okay. So the ith times in the ith direction. Okay, minus, put the minus there. That's for the minus j. Okay, and this is going to be d dx of negative y squared, which is going to be nothing. Okay, minus d dz of xz, okay, the jth direction, plus, okay, dd, this is the last one. This is the one I kind of started with. d dx of xyz, okay, minus, okay, minus, what do we got here? D dy of xz. It's not d, it's partial, sorry. Partial of xz with respect to y. And that's k. Okay, so let's see what happens here. Well, when I take the partial with respect to here, I get negative 2y. Okay, with respect to y, that's a y. Okay, partial with respect to z, that's just going to be minus xy in the ith direction. Okay, minus, this is going to be 0. Okay, minus 0 minus this thing in the z direction. Okay. So, sorry, in the partial on z in the jth direction. So d dz of this is going to give me x. Okay, in the jth direction. Okay, nice. The minus. Right? Okay, and then this guy here, partial with respect to x, so that's going to be yz, minus partial with respect to y, well, that's just 0. Okay, let's clean this up. This is going to be negative 2y minus xy I, okay, plus xj, plus yzk. Okay, and that's the curl of f. Now, theorem. Okay, the curl of f, the curl of f is 0 okay, that is no, it's not f, it's del f, sorry. del f, if I take the curl of del f, okay, the partial of f, okay. Okay, so the curl of del f, which is f, and that's still capital F. Curl of, I'll just put f equals del f. There we go. Okay, the curl of f equal del f is 0. Okay. That is the curl of del f equals 0. Okay. If f is conservative. Okay. This means that if there exists this an f for which the del of f equals f, then the curl of f, this means that if there exists an f for which del f is equal to f, and f is conservative, then the curl of f is equal to 0. Okay, so just basically, we get the curl of f. If you give me the vector field, and I find that the curl of f is 0, okay, then I know it's conservative. Then I know the original vector field was conservative. Okay. Number 2. Okay, show that the vector field f equals x, y, z equals y squared z cubed I plus 2x y z cubed j plus 3x y squared z squared k is a conservative vector field. Okay, so sorry, this should not be equals. This is just f of. Okay, so now why is this important? Why is this powerful? Well, if you remember back to how we were proving that things were conservative before, we didn't know how to deal with it with a third variable. Okay, we could only deal with it with 2 variables, right? Now think about what would your kind of your matrix look like if you had only 2 variables, right? If you had just, f, x, y, right? What would your matrix look like? Right, so if you had f, x, y, then your matrix would be I, j, k. You would have dx, okay, sorry, ddx, ddy, ddz, right? And then you would have x, some p, we'll say p, q, and then 0 would be r. R would be 0. So you'd have some function f, if you did the curl of a two-dimensional function, okay, with only two variables, say this is the curl of f of x, y, right? Okay, the curl of f of x, y, we would have this 0 here. Okay, so how would that affect things? How would that affect things to have that 0 in the kth direction there? Well, let's see what happens here, right? So we would have right, so let's do this. Okay. So let me think about this for a second. And we would have a 0 here too, I think, right? Because you can't take the partial with respect to, you would just have a 0 here as well. You can't take the partial with respect to z because you don't have a z. Okay, the partial with respect to z is always going to be 0. I guess that's fine. I mean, as long as we know that the partial with respect to z is always going to be 0, we could still have it. Okay, but just know that it's always going to be 0. Why? Because if I take the partial with respect to z, is p or q going to have any z's in them? No. Let's just write it out, and then I'll go through the logic. Okay, so we're going to say, okay, d dx, right? So we're going to do the ith one. So this is going to be d dy of 0 minus d dz of q. dz of q, okay. But again, we'll see that whole thing is going to go to 0. Okay, minus the jth is going to be d dx of 0. dx of 0. Okay, minus d dz of p. d dz of p. Okay, and then plus. Okay, and then we've got, okay, dd, what do I want here? Okay, so d dx of q, yep, d dx of q minus d dy of p. Okay, there's a j here and a k here. Ooh, that's interesting. Okay, so so this d dy of 0, that's just 0. Okay, but d dz of q, but again, what is q? Q is, it's qxy. So if q is just in terms of xy, then when I take the partial, think of having like a bunch of x and y's here. Okay, when you take the partial with respect to z, that whole thing is going to go to 0 because it's treated like a constant. So this is 0, right? So that's I. So this is just 0i. Okay, this works the same way. This is going to be minus 0 minus 0. Okay, because when you take p is also just xy's. Okay, take the partial with respect to z, right? You get 0. Okay, partial with respect to z, we're going to get 0. Let me write this out funnily. Okay, so just the partial of q of xy with respect to z is equal to 0, and the partial of p of xy is dz is equal to 0, so that's just 0. Okay, minus 0. Okay, j. Okay, plus, okay, plus dq dx minus dp dy. Okay.
Interesting. Isn't q 2xy z to the cubed?
No, this is an aside.
Oh, okay.
I'm just showing you why this is important. Okay, why is it important that we can do this? Okay, and I'm saying, well, we went from 2 dimensions, right? And then we're moving into well, it's actually 3 dimensions, but we're moving from 2 variables to 3 variables. This is for 2 variables, and I want to just make the analogy for 2 variables, for 2 vars, why this is important, how this applies, and how we're building a connection to things that we've already seen. Well, where have we seen this before? Where have we seen this this is no longer a vector. This is kind of a scalar in one direction. This is in one, okay, in one direction. Why? Why is it one direction? Because no longer does it have an ith or jth component. All right, this is just going in one direction. Well, if you wanted to talk about distance in one direction or a vector in one direction, okay, then you think of that as kind of a linear, okay, or a scalar. Okay, so we just turn this in three dimensions, this is a vector field, but in 2 dimensions, it ends up giving me a scalar field. Okay, and where have we seen this before? This dq minus dx. dq dx minus dp dy. Well, didn't we see that was true when we looked for things that were conservative before? Right? When we looked at things that were conservative before, what did we say? We said, oh, well, if we say that this thing is what would this thing have to be equal to if it was conservative?
To 0?
Yeah, exactly. This thing would have to be equal to 0, or we could say that dq dx was equal to dp dy, right? So we already know this from our prior understanding that it's conservative if this is true. Well, yeah, because now we've broadened it. We've actually broadened it. Now you kind of know where that came from, right? You're just like, where did this come from? Where is it coming from? And it's coming from the curl here, okay? The curl. We just limited it, okay? If this is true, then it's conservative. So now we're taking this idea of being conservative in two variables, and we're saying, well, what happens when we expand it to 3 variables and we get this, 3x3 determinant? Okay. You could also think of it as, just a 2x2 determinant if you really wanted to. Okay. That you could say, well, this is ddx, dy, and then this is p and q. I mean, it's kind of the cheap way of doing it. I'm just saying, what happens when I take the determinant of that, right? This 2x2. Okay, I still get the same thing, okay, but I have to set that equal to 0, and then it's conservative. Okay, so now we're going to generalize this to the 3rd dimension, okay, the 3rd variable, fourth dimension, basically. Okay, so this is a 3 variable vector field, okay, vector field in 3 dimensions. Okay, and so we're gonna show that this vector field is conservative by setting the curl equal to 0. If the curl comes out equal to 0, then it's conservative. So let's see if that works. Okay, so let's look at the curl of f for this guy. Going back to the problem, we have I, j, k. We have ddx, ddy, ddz. And we have the ith term was y squared x cubed. The jth term was 2x y z cubed. And the kth term was 3xy squared z squared. Okay. So if the curl of f comes out to be 0, then we won. Okay, so let's see what we get here. So the curl of f, and again, why is this important? Because we couldn't deal with this before. We could only deal with stuff with 2 dimensions. Okay, and now with two variables. Now we can deal with stuff with 3 variables. That's why this is important. Okay, so the curl of f is equal to, okay, and again, maybe I'll do some of this in my head, right? So can I find if I find the determinant of this cofactor, then what's this going to become? This is going to become 6, right? 6xyz squared. So this is 6xyz squared minus, with respect to z here, well, look at that. Isn't that, if I take with respect to z, isn't that also a 6xyz squared? Very nice. Okay, that's in the ith direction. I've got my first 0. Okay. Minus, okay, let's do it in the for the j, that's going to be d dx. Okay. So that's this guy and this guy and this guy and this guy, right? Okay. So okay, so take d dx, or the partial on x of 3xy squared z squared, and we get 3y squared z squared. Now let's do the partial of z on y squared x cubed. Oh, it's not x cubed. I'm sorry. This is z cubed. It's z cubed. I wrote that wrong. Is it correct in the original? Yeah, it's correct in the original. Okay. So that's z cubed. Okay, so I'm like, why is it not coming out? So now it's going to be the same thing. It's going to be 3 to bring the 3 down. So that's 3y squared z squared. Okay, and that's my, these are going to cancel out. That's going to be my second 0. So then j, right? Okay, plus, let's see what happens when we do the last ones here. Okay, so this is going to be partial of, we're going to do this, partial of, nope, other ones. Partial of x with respect to this guy, that's 2yz cubed. And the partial of y with respect to y, that's 2yz cubed. Okay, and that's my third 0. So 0, 0, 0. So what do we know? We know that f, the curl of f is equal to 0, which implies that f is conservative, which implies that there exists, okay, an f such that del f is equal to f. Boom. Just means that we can find it, okay? It's good to know if you can find that or not, okay? We don't know what it is, but we do know that it exists, okay? Okay, now if you're like, well, what is it? You know, what is it? Well, all I can do is tell you that what we could kind of work backwards here. To, I mean, if we really want to, let's do it. Let's try to work backwards and see if we could find out. Does it even exist? Yes. Is it worth going for? Yes. Okay. So what is f? What is f? What's the parent function going to be here? Well, f is going to be fx plus. So sorry, f is going to be fx in the ith direction plus, because it's del of f, right? Okay, and then fy in the jth direction plus fz in the kth direction, right? Thinking. Okay. Let me make sure that's right. Yeah, yeah. Okay. Oh, it's the del, yeah. Goes the del of f is equal to f, yeah, that's right. Yeah. It's equal to the partial. Yeah, so we need to find out what is f, yeah, okay, I'm good. Okay, so what were we given in the beginning? We were given what is f? I guess I can just look at my notes instead of scrolling all the way back. Okay, so f was equal to y squared z cubed I plus 2xy z cubed j plus 3x y squared z squared k. Okay. So now I'm going to ask myself, okay, well, what if the partial of f, let's do this. If the partial of f with respect to x is equal to y squared z cubed, then what would the original term have to be here? Well, then that doesn't involve an x, right? So that would have to be x y squared z cubed plus, you know, blah, 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 some other terms, right? That's the only term that I can come up with. Okay, so what about, well, maybe I'll look at the other terms. What would the other, there would be, this term involves x, y, and z. There would be terms that don't involve x, y, and z. But again, I'm just going to do like that. Just know there's extra terms here. Okay, there's terms that could be, I mean, there's a lot of extra terms. There's terms that could be just xz. There could be terms that are just y, yz. There could be terms that are just g, h, I, j, k, l, maybe l, m of, what did I not use? I didn't use x and y. X, y, this is an m of x, y, plus, I'm not going to do this on all of them, okay? Plus p of x, plus q of y, plus r of z, plus c, right? So here's all the extra stuff that could be a part of it. The good news is that it's not a part of it, okay? So just keep that in mind. Because when we take the partials of the other ones, we're not going to come up with anything else. So let's do that. And like basically this stuff goes away. This stuff goes away. Okay. So when we take the partial with respect to y, okay, of f, then we would have gotten 2xy z cubed. Okay, so how am I going to integrate this thing? This is going to become y squared over 2, right? So integrate this. This goes to 2xy squared over 2 z cubed, right? So the 2's cancel, and lo and behold, I get the same exact thing out that I got before. Oh, that's nice. Plus, and then I can put all that stuff. There you go. There's all the stuff. Okay. Gosh, that is not looking good. The 2's cancel, right? Boom. Okay, and so maybe I'll rewrite this. Okay, this equals x y squared z cubed. Okay, plus blah, 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 blah. All the extra stuff that could be there, but isn't. Okay, why am I going to know that it isn't? Because I'm going to come out with the same thing 3 times. That's how I know that it's not. I kind of gave you the punchline there, but before I told the joke, but that's okay. Okay, so 3xy squared z squared, right, is equal to this, and then well, let's integrate on z. Let's integrate on z here, and so that's 3xy squared z cubed over 3, cross, and we get xy squared z cubed. So were there any extra terms? No, there weren't. All this stuff is gone. Okay, so what's the only term that we have? Well, the only term that we have is that f was equal to, okay, f of x, y, z was equal to xy squared z cubed plus some constant. Could have been some constant, okay? We just don't know. Okay, but there are no other like funky xz terms or x. It's just one thing. So, and this thing is our parent function, and so we could find it. For f. Okay, so there you go. Okay. And we could do that because it's conservative. If it wasn't conservative, we couldn't do this. Only because it's conservative could we find that. And do we want to look for something that could potentially not be there? No. So what are we going to do? We're going to calculate the curl. And if it's equal to 0, then we can go ahead and find our parent function. Okay, so let's go to divergence now. What does divergence mean? Okay. If f equals to pi plus qj plus rk is a vector field on R3, and dp dx, dq dy and d rdz exist, then the divergence oh my gosh, I can't write. Then the divergence of f is the function defined by the divergence of f is equal to dp dx plus dq dy plus dr dz. Now notice what's not there. What's not there is ijk, because this thing is not a vector. This thing is a scalar. We call this thing a scalar field. This is a scalar field. Okay, it's not a vector. Okay. Okay, so once again, this one's a pretty easy proof. Okay, but we're going to say that if we have the gradient function is equal to ddxi plus ddyj plus partial on zk, okay, if this is true, okay, if this, then del dot f, okay, del dot f, what's that going to be? That's going to be this thing, ddx, ddy, ddz, dotted with pqr, right? Make sense? It's a p, right? So dot that with pqr. So what's our dotting here? Well, we're dotting these functions, these partial derivative functions, and we're partialing the p, q, and r. And if we dot that, then we're going to get a sum, right? It's going to take two vectors. The dot product takes two vectors and gives me back a scalar. Okay. So this is ddp dx plus ddq dy plus ddr dz, and that's equal to what? Not everybody at once, okay? What does that equal to? There you go. Thank you, Armando. Yes, the divergence of f. Okay, is the divergence of f. There you go. There's your little, okay? So there's our thing. Okay, so the divergence, okay, is equal to that. Okay. Go away, go away. I want to talk to you. Okay, so yeah, let's do example 3 here. Let's find the divergence of this thing. Okay, so if f is equal to xzi plus xyzj minus y squared k, find the divergence of f. Okay, find the divergence of f. There we go. Okay, so what are we going to do? Well, we're just going to take the partial of the first one with respect to x, partial of the second one with respect to y, and the partial of the third one with respect to z. Oh, okay. So this is actually, the divergence is a whole lot easier to calculate than the curl, right? Because you don't have to do a 3 by 3 matrix. Okay. Well, this one's actually a lot faster to calculate. Divergence of f is going to be ddx of xz plus ddy of xyz plus ddz of negative y squared. Okay. So this is going to be z plus xz, okay, plus 0. Okay, and then maybe I'll just factor out the z. Z times 1 plus x. Okay, and that's the divergence of f. And again, it's a scalar field. Okay, it's scalar. Okay. So the divergence of f was equal to that. Okay, okay, nice, nice, nice.
Can you scroll back up a little bit, please?
Okay, like that. Okay, so let's do a theorem about this. Theorem. If f equals pi plus qj plus rk is a vector field on R3, and P, Q, and R have second order continuous, sorry, to have continuous. Nice. Second order partial derivatives then, okay, then the divergence of the curl, that's interesting. We're going to take the divergence of the curl. Oosh, oosh. Curl of f is equal to something. Okay, what the heck is this? Well, where we found the curl before? What did we find the curl of before? We found the curl of this guy. It was the same dude, okay, in number 1, right? So this dude here, we found the curl of that, right? We found the curl of that. So if f is equal to, somebody post something. Are you talking to me? Are you talking to me? Okay, so if we have f, right? F was equal to f of x, y, z was equal to xzi plus xyzj minus y squared k, right? Okay, so what was the curl of f? The curl of f was equal to negative 2y minus xyi plus xj plus yzk. This is from number 1, from example 1, numero uno, okay, from number 1. So we have that. So let's take the divergence of this thing, okay? So the divergence of this thing, what's the divergence of this thing? The divergence of the curl of f. Okay, so what are we going to do? We're going to take d dx of the first thing here, negative 2y minus xy, okay, plus d dy of this thing, which is x, okay, plus dz of this thing, which is just yz. Okay. Now what's this going to become? This is going to become negative y, because this thing's going to go to 0. So this is negative y. This is going to be 0, right? So plus 0. And then over here, we're just going to go y plus y. Oh, look at that. It equals 0. So in that one example, it equaled 0. So why is it going to equal 0? Well, let's prove this. Let's prove that it's just not this case that works. Let's prove that it works for every case, all cases. So let's do a proof of this. Proof. Okay, so Armando, I think you were right. It was 0. Okay, but now let's prove that it works not just for this one case, but for all cases. Okay, so we know what the curl of f is. I know how to find the curl of f. What is the curl of f? Curl of f is dr dy minus dq dz, right? I minus dr dx minus dp dy j. I think that's right. Nope, dp dz, sorry. dp dz j plus, okay, dq dx x, okay, minus dp dy, I believe. That's right. Okay, so I know what the curl is. Nice. So let's take the divergence of the curl. See what happens here. The divergence of the curl. Okay, so this is going to be the derivative with respect to x of this thing, dr dy minus dq dz plus, okay, nice. Okay, plus what? Plus, is it okay if I distribute the negative here to retain the positive sign? If I distribute this negative, are you guys going to be okay with that? Distribute the negative, and then this becomes minus plus, right? So, I mean, just keep that in mind. Okay, so this is going to be d dy of minus dr dx plus dp dz. Okay, so all I did was distribute that negative, and then took the partial with respect to y. Okay, and then plus, okay, dz, partial with respect to z, of dq dx minus dp dy. Okay, so now I'm going to distribute this thing. Okay, basically what I'm doing is I'm taking the partial with respect to x, partial with respect to r, partial with respect to y. Okay, interesting. Okay, minus partial with respect to x, partial with respect to q, partial with respect to z, partial of q with respect to z. Okay. So we're taking partials of partials now. Okay. So plus, this is going to be partial of y, and then, right, minus partial of r, partial of x, plus partial of y times partial of p, partial of z, plus partial of z, partial of q with respect to x, okay, minus partial of, minus, okay, partial of z of partial of q with respect to y. Okay. Now, okay, why is it important now that the theorem, okay, said that we have continuous second order partial derivatives? Because f of xy is equal to f of yx when what? When the function, okay, f, okay, is continuous. Okay, so you can say, oh, the partial in one direction is the same as the partial in the other direction, right? I mean, what does this mean? This means d dx of df dy is equal to d dy of df dx, right? So this, all it's saying is saying, look, we took the partial, you can take the partial in any order, and as long as your function was originally continuous, which means your second partials are continuous as well, then you're good. Okay, so then you're good, right? Then you can do it in any order, which means, okay, going back here, that these are all going to cancel, right? So the partial of x and the partial, taking r, let's write it like this, taking the second partial of r with respect to x with respect to y, minus the second partial of q with respect to x with respect to z, plus, well, I'm going to make this a minus because it's a negative, minus the second partial of r with respect to y with respect to x. These are going to be the same thing. They're going to cancel out. Done. Okay. Plus partial of p with respect to y and z, second partials. Okay. Plus second partial of q with respect to z and x. Z and x. Oh, look at that. Another one bites the dust. And then this is minus the partial of second p over partial z partial y. Okay, and that's the third one. Boom, gone. And so since they all cancel out, it's 0. Yeah. Proved it, not for a specific case, but proved it for the general case. There we go. That's good. Okay. A lot of proofs. A lot of proofs today. Okay. Okay, let's go over, okay, one other thing here. Whatever. Okay, let's look at the vector forms of Green's theorem. Okay, so like what the heck was Green's theorem, right? So long ago. Okay, like what the heck was Green's theorem? That was just in the previous section. Okay. So, okay, what did Green's theorem say? Well, Green's theorem says, okay, symbolically, that if we have this thing, C, of P dx plus Q dy, then that was equal to, okay, the enclosed domain, right, the C and D. And we could change this line integral. Okay, we can change this line integral, going positively oriented line integral, okay, around a closed region. We could change that into the area contained in that region, the double integral, right, of P dx. Of dq dx minus dp dy dA. Okay, that's what we could do there. Okay. So that is Green's theorem. Okay, so okay. How do we get the vector forms of Green's theorem? Okay, so this was Green's theorem. Okay, then we could say, hey, well, what is this thing originally? This thing is originally looked like this, f dot dr, okay, is equal to this thing, right? Where, okay, f is equal to, we're going to say pi plus qj. We're only going to do it in 2 dimensions here. Okay. Okay, but we saw what? We saw that when we take the curl of f, we get what? Okay, what happens when we take the curl of f here? We did that already. Right, okay, thanks. Okay, the curl of f. When we had 0 k here, what happened? We're only left with that one term, right? We're only left with the curl of f ended up being dq dx minus dp dz, or sorry, dy, okay, k in the kth direction, right? Okay, nice. Okay, so let's take this. Let's dot this curl with k and see what we get. Okay, so if I take this curl and I dot it with k, what happens? Okay, so if I take, let's say that we take m in the kth direction and we dot that with k, what happens? What does it equal? What does that equal? We're going to dot this, right? Well, think of it like this. This is 0, 0, m, dotted with what? Dotted with 0, 0, 1. Okay, well, what's the only thing that's going to survive there? What's the only thing that's going to survive from that dot product?
M?
Yeah, exactly. Very good. Yeah, m. That's the only thing that's going to survive. So what I want to represent this thing in vector form. Okay, so how do I do that? Well, I just say, hey, you know what? Let's just do d of the curl of f dotted with k. Okay, dA, and that's how I can represent, okay, the Green's theorem, okay, in vector form using the curl. There's an L there I left off. Okay, so this is just another way to write Green's theorem. Okay, because the curl of f dotted with k is this thing. Okay, that is this here. Okay, and so this is just the vector form of Green's theorem. So is equal to this. Oh, okay, so we can find the curl and then just look at the kth power and then the kth term, and that gives me the curl. So this is just another way to write Green's theorem. Another form of Green's theorem let's capitalize the green, give credit where credit is due. Green's theorem, another form of Green's theorem in vector form. Okay, so okay, one last thing that we should discuss, okay, is, okay, let's say that we have a line integral, okay, and it's going around, okay, somewhere. We can get, on this line integral, we can get a tangential vector. Okay, we get our tangential vector. I'm going to call that T of t. That's my unit tangent vector. Okay, my unit tangent vector there. And then I could get an n of t. I could just get, well, if n of t, capital N of t is my unit normal vector. Okay, I don't want that. I want little n of t, which is just any normal vector, any normal vector. So we'll just call this n of t. This is just a generic normal vector. Okay, normal vector. Okay, this thing is my unit tangent. This thing is just a generic normal vector. Okay, so, okay, and we're going to say that the line integral of the normal, okay, we say that the n of t could also represent, you know, some normal vector field too. So the line integral of the normal component of f along C can be expressed as, okay, as what? It can be expressed as, okay, positively oriented line integral f dotted with n, okay, some normal vector, okay, and then ds, okay, and we could say that that is equal to, okay, that is equal to the double integral of d, okay, interesting, okay, of a d of, okay, I'll make sure I don't screw this up. Uno momento, por favor. I like that. Okay, that's good. That's good. Okay, dp dx plus dq dy dA. Okay, which by our definition is equal to what? The divergence of f dA. Okay, now I'm only using two variables there. Okay, you could generalize this to 3 if you really wanted to. Okay, so okay. It's interesting. It's very interesting because, like, what is the normal? I don't know. I'm just going to kind of play around with this for a second. Like, let's think about this for a second. Right? We have a tangential vector field, right? So, and then what would be a normal vector field? So if we have just f is equal to pi plus qj, then what would be tangential? Well, it would be b. If I took the partial in the x direction, partial in the y direction. Okay, so partial in the x direction. Partial in the y direction. Okay, that gives me t. Okay, but if I want the line integral of the normal component, then we take and we dot this with what? We dot this with ij. Right? We would have to dot that with ij. No. And then we'd end up with the same thing. So yeah, I don't know. I was just messing around. Okay, I think we'll stop there for today. Okay. Welcome.
I was wondering if you could go over one more homework problem.
Sure. What's the homework?